Happy Tuesday. All right, we're sharing, we're Zooming, we got everything. So I put up a homework, and a few of you have started working on it, maybe? Yes, already? No? Well, I was just answering some questions about it, and I was going to talk about it on Thursday, thinking that no one would have started it yet. But if you started it, then that means I need to talk about it today. So why don't we start there and give you, there's two things that I wanted to make sure that I talked about because we had done it not that consistently before. One is in terms of model comparisons involving count distributions, and the other is in terms of just setting up this model. So homework 3, I gave you the background of the story, right? My son goes to food school, although he is sick right now at home with dad and will not be going tomorrow as usual. But food school is a food desensitization program where they're trying to get him so that he won't like pitch a fit if something gets on his plate. He learns to look at it, touch it, eventually work his way up to eating it kind of thing. So they're working with him to try and gain some flexibility. And so the story for this homework is about preschoolers who are involved in food school or not, and they also have differences among those who are involved in how many sessions they've attended. And the outcome you're predicting is the number of new foods tried over an observational period of 20 days. So this homework has more predictors than usual. It has food school, which is the thing I wanted to talk about, whether or not they have older siblings, whether or not they have younger siblings, and whether or not their parents both work full-time. So those three are sort of covariates / moderators. And you are being asked first to compare the fit of a Poisson empty model to the fit of a negative binomial empty model. And because of the debacle between SAS and Stata, I have hopefully figured it out. I spent extra time trying and doing each of your homeworks, trying to make sure that it would work. So there are certain questions where I'm saying round it to the nearest 0.10, because that was the only way I could make the programs agree. So that happened for the Pearson chi-square over degrees of freedom statistic. It also happened for one of the chi-squares. And if that doesn't work, you may have to cheat and be like 0.1, 0.2, 0.3, because they are so close, but like they're not exactly the same. And so I apologize for that, but there's only a few questions like that will be the case for. So two things I wanted to talk about. Number one, how do you compare the fit of these different distributions? In this case, Poisson is nested in negative binomial because negative binomial adds an extra stretchy factor that allows the variance to become a quadratic function of the mean rather than a one-to-one function. So you can take the -2 log likelihood from the Poisson model and take the difference between that and the -2 log likelihood in the negative binomial model. So in the count example that we did, for instance, here is this was the number of mean things said story where we looked at counts. So here's the Poisson model. I'm going to demonstrate this for you. So there's my -2 log likelihood. Come on, make it bigger. So this is -2 log likelihood. Here, insert model. So order matters. In these tests, it's always the model that's simpler minus the model that's more complex. Fewer minus more. So the Poisson -2 log likelihood was that number right there. We'll do a Stata version down here since they give you something different. The Stata version is, oh, do I have that in here? Yes, I do. It's this one right here. There's that number. Okay. So for negbin, that's the next one. Let me grab the -2 log likelihood and the log likelihood. So this is for negative binomial that adds the stretchy factor. Oh wait, wrong one. Thank you. Yeah, that goes there. So in SAS, model fit is given to you as -2 times the log likelihood. whereas in Stata it's given to you as log likelihood. So let me go get the version from SAS. So I have a text box here that tells you what happened. I'm showing you how I got this. All right. So we have the difference. That minus 2 log likelihood in SAS for the Poisson model, minus the minus 2 log likelihood for the negative binomial model. You will know you got the order wrong if this difference is negative. It can't be negative because chi-squares don't have negative values. Likewise, diff times minus 2 is what this needs to be in Stata. So I take that one minus that one times minus 2. And as you can see, they agree very closely. Here, let me see if it agrees even more. Yeah, not a, see, this is my life right now, okay, between these two programs. So, very close, but not exactly. So this number right here, either way, 327, what the hell is that? That is a test statistic. You've got 4 choices. Is that a T? Is that a Z? Is that an F? Or is that a chi-square? This is a chi-square. So then, to get the p-value, chi-dist, it wants the chi-square value as one argument. The next argument is the degrees of freedom. This is the number of things that are different between the model. So the number of model parameters added to the one that's more complex, which we can do 1. And that's p to the minus 73. Either way. So I think, do I even have that on? Yeah, I copied that in scientific notation. Now here's the extra tricky part. This is the p-value for degrees of freedom equals 1. In your homework, I'm asking you for the p that goes with degrees of freedom as a mixture of 0 and 1. The reason for that, whenever you are testing a new parameter that is on a boundary, so this scale factor can't go negative. It has to be a positive number. If this mixture of 0 and 1, you take your regular p-value and you cut it in half. So yes, e to the minus 73, either way, which the homework system will take as 0. In Stata, it does this for you if you run NBReg instead of GLM. It spits out right here, likelihood ratio test of alpha stretchy factor equals 0. Chi-bar, meaning chi-square with a mixture distribution of 0 and 1, is 327.01. So that is this number right here that I did by hand. In Stata, you can also use lrtest as a command to get this for you. I had problems with these models. Sometimes it wouldn't do it, thinking it wasn't they weren't nested when they were. So you can always jump into Excel and do this. So that's one thing, how to compare distribution fit. In general, so I'm labeling these fewer, more. If the difference between nested models is significant, which one fits better? So your choices are the one with fewer parameters or the one with more. Negvin, that's your vote? Yeah, the one with more. What we're asking is if we added parameters, did minus 2 log likelihood go down, because minus 2 log likelihood is badness. Log likelihood is backwards. We want it to go up. Log likelihood is height. Minus 2 log likelihood is lack of height. Either way, it's the difference we care about. So if the model that has more parameters fits significantly, the difference is significant, the model that has more is better. Question?
I had a question about, like, can you also compare AIC from model to model?
If they're nested, if they're part of the same distribution family, yes. So like you can't do normal versus Poisson,
Okay.
but you can do Poisson versus negative binomial because they're part of the same thing where one is a subset of the other. Yep. The other way of thinking about the significant result, the model that has fewer parameters fits significantly worse. So if the difference in models is significant, the one with more parameters fits better, the one with fewer parameters fits worse. If this difference were non-significant, let's say the difference were like 3. So my p-value is 0.08 for that, for instance. Then how would I describe these two? The one with more parameters fits not better. You cannot say worse. It's not better. You added something, it didn't help enough. But it helped at least this much. So when you're talking about log likelihoods and minus 2 log likelihoods, when you add something, they get better. The question is better enough. When you're talking about AIC and BIC, they can actually get worse because they don't like it when you add unnecessary stuff. So if the result is non-significant, the model that is more complicated fits not better, and the model that has fewer parameters fits not worse. There are a few times in statistics when not worse is going to be a question. Usually it has to do with the fit of some kind of covariance matrix. This is something I'm developing a lecture for right now that may or may not be ready for you on Tuesday, to be honest. It's not looking good right now because Huey needs to get better. Because he wants me to sit and watch Mickey Mouse racers with him all day long while he's sick. It is not acceptable for mommy to go sit in her office and try to get her lecture done. So that was yesterday. You don't believe me? I took a selfie. This is me and him on the couch yesterday. I am tired of watching Mickey Mouse racers, as you can tell. That's what that face says. And this is him putting himself down for a nap voluntarily inside his little house. He was so tired, he just sat down. He's sitting there like this. You want a pillow, buddy? Yeah. Do you want a blankie? Yeah. Thumb in the mouth. Yeah, so. He will be 5 on Saturday. We already went to the dollar store and got our party swag for our children, so I really hope we get to have our party on Saturday. This actually happened when he turned 2. We had to cancel his birthday party because he had the flu. So, yay, influenza. But his dad sent me some pictures today. He's doing better. This is the piñata for his party. It has a place of honor on the dining room table since we bought it like 2 weeks ago. And he is eating what he calls pancakes. So, yes. So yeah, maybe I'll have a lecture on Tuesday. It's unclear. But Jonathan always reminds me, you know, if you have to cancel class, they're not going to be mad at you, right? You know that, right? But no. So, all right. Does that help answer your question about this? Anyone else have questions on model comparisons? The reason that we haven't done much of these, so there's actually 3 different ways to test significance of more than one thing at a time. The thing that I keep having you do is a wald test. That's the contrast statement or the test statement. That is the multivariate analog to the t-test that shows up on your output. It's whether or not your slopes are different than 0. Slopes can be positive or they can be negative. They're not bounded. So wall tests work for all instances across all models, and that's why we do it that way. This likelihood ratio test, this is what you have to do when you are making decisions about the variability part of your model, such as whether your variance exceeds the mean, such as what we're doing in multivariate next week, such as whether or not you need random effects in multi-level models. And you can screw these up because these are only allowed in certain combinations of things. So because these are screw-upable, I try to avoid them unless I have to do them. But we can't do wall tests for variance-related terms because variance-related terms cannot be negative. So the boundary thing makes it so we have to do a likelihood ratio test instead. If you want to get more on the technical side of how these things differ from each other, in the Agresti book in chapter 3 or 4-ish, he has an extended discussion of these two things and also a score test, which is another way of testing something against zero. So we haven't had to do these much, but we will start doing them more coming up. Okay. Any questions on likelihood ratio tests? All right. Then the other thing I wanted to go over with you guys is the coding for this. So we haven't done an example like this in class before, but I believe you to be capable of extrapolation. But I wanted to give you a head start. So we have a variable in your data set that is called numSchool. It's the number of sessions of food school that a child has been to. So let's say that we have 0 sessions, 1 session, 2 session, 3 session, 4, 5. Okay. I am asking you to take that variable and fit what I would call a piecewise model through it. So some of you may not have seen this before with me. Those of you who've done multi-level or longitudinal, I'm pretty sure you've seen this. We did this last semester in 6242, but if you were not part of those, let me show you how this works. What I'm asking you to do is to create 2 new variables. I'm abbreviating these things here. One is whether or not they're part of the food school program. So that's a qualitative distinction, right? So this person is not part of the program. Anyone else that has more than 1 session is part of the program, okay? Now, how effective is the program? Logically speaking, the only people that can participate in saying how effective the program is are the people who are in the program. Is more better? That's the question. So I wanted you to create another predictor for how many sessions that they've had, if any. That means people who haven't had any sessions still get a 0, but I wanted to center it at 1. So your columns would end up looking like this. Okay, Jeff, are you squinting or are you looking puzzled?
Yeah, does that mean that local attendance once is similar to
Ah, so you're worried about this 0 right here? Do not worry. Because your model is going to have both of these things in at the same time. So this variable right here is going to differentiate between these 2 types of zeros. Somebody who has not attended food school has a 0 on both. Somebody who has attended at least 1 session of food school gets a 1 on the first one. So the difference between the effect of any school, so to speak, is the difference between children who have no sessions and 1 session. So this predictor in the model distinguishes these 2 kinds of zeros. From there, this variable shuts off, so to speak, and this one turns on to distinguish these types of ones. So this is the predictor analog to a hurdle model. Remember hurdles? A hurdle model, we'll talk about this today. It's a way of dealing with 0 inflated outcomes. This is the predictor analog. where I have two kinds of kids here. I have kids who've never participated in this program, and I have kids who have. And among the kids who have, I want to see if more participation helps. So you can think of it as a piecewise model that differentiates 0 from 1 as one slope, and then the slope of more than 1 as the second slope. So you'll have to figure out how to write code that does this. I think you can do it. So this is the variable that we started with, and these are the two that you have to create. Then in testing moderation. So one of my hypotheses is that the effect of these two variables depends on whether the kid's parents both work full-time. So that idea of moderation by full-time has to happen with both variables because both variables are required to piece apart the effect of food school. So that should get you started at least. And if you have questions about how to set up the models, I'd be happy to entertain them. I'd be happy to waste a class entertaining them, in fact. That way, if I don't have my lecture done, I don't have to feel bad. Or even give you open time in class to work on homework. That's another option. We may end up doing that if I can't get my shit together. I'm sorry. So because of Mickey Mouse roaster racers, as he calls it. Yeah. He sings with the headphones on, and he says, Mickey Mouse roaster racers. I'm like, there's chicken on the show? What's a roaster racer? No, it's a roadster racer. Not a roaster, but anywho. This is my life right now. Okay. Otherwise, it's fairly similar to linear model stuff we've done before, and the only count aspect of it is just comparing fits of distributions. So, any other questions before we adjourn this topic and move on? Not right now. Okay. Then, let us look at some new stuff. Things that are done. By the way, likelihood ratio tests, I pulled up this slide. These are described in lecture 1. This is slide 17 and 18. So that's where I initially presented it, but we hadn't visited it in a while. All right. So we were talking about skewed outcomes that aren't counts, right? Got to that much? So what other kinds of distributions can you use for continuous outcomes that aren't normal? That's the topic. So this is slide 10 on lecture 3. All right. So if you have outcomes such as response time or money, things that are continuous values, they're not just integers, but they're non-integers as well. They may not be normally distributed. Normal means continuous, like these are, but it also means that it ranges from positive to negative infinity, and that it's symmetric, right? That's a pretty tough ask for variables like this. So what else can we do instead? There are two distributions that are more ideal for these types of outcomes that are positively skewed continuous outcomes, log normal and gamma. The only catch is that these distributions do not include zeros. So if you have a positively skewed outcome that does have zeros, you got to do something else. So stay tuned for that. If you can't figure out what to do, if you come across a problem that is not fit well by any of these choices that we've talked about this semester, or you're concerned about outliers, quantile regression is one last thing that we have in our disposal. So here are some pictures. This is what log normal looks like. Log normal is saying that the log of the outcome is normally distributed. Super handy because you can just log your outcome and fit this model. So I'm going to use this a lot in future classes because the choices that we have for multivariate models are not nearly as many as for univariate models. The parameterization in Glimix is somewhat confusing, so just keep in mind that it's not any different than what we've been doing so far. We predict the log of the outcome, and then you have to unlog it, exponentiate it to get back to the original outcome. Gamma is also something that's made for continuous outcomes. It has a scale type parameter that translates how the variance and the mean relate to each other, but it is an estimated parameter very similar to the k in the negative binomial, so that it's not as restrictive as other models. So that one I've seen less, but it does the same thing. It's designed for positive outcomes without zeros. Question?
Is there any model like this that uses like Laplace?
That's like what?
Laplace?
Laplace is a method of estimation. If it's a distribution, it's the first I've heard of it.
Okay.
So what is the context in which you're asking about
I was
Laplace?
just looking at, I was doing an RA thing, and they mentioned that, like, what is this for? And they talked about it, and I haven't come across that before.
So
We don't have to know that.
yeah, it's a type of maximum likelihood.
Okay.
That's easier than what it's going to be for these models when we get to multivariate. It runs faster. There's my short answer. But, so were we looking at the example yet? I forget where we left off. Predicting house prices? Did we do this?
This is when you talked about the really expensive house.
Yes, then Lisa got off the rails a bit and we started talking about my house hunting trips. Here's a tip. A mistake I made when I was a junior faculty member in my first job: don't take out 3 mortgages to buy a house. If you need 3 mortgages, you can't afford it. There's a tip for you. Do you know how 3 mortgages works? Because I had 5% down, and then I took another loan that was for another 10%, and a third loan that was for like the other 5% to piece together 20% down through multiple loans. Very bad idea. So please, if you're thinking of buying a house, if it takes more than 1 mortgage, you can't afford it. So many years later, I climbed back out of debt after the house sold. But it was a very intense period in my life. So yeah, I take this personally. So we were looking at this set of 100 houses. This is from your Agresti book. And looking at what would potential conditional distributions be. So I'm showing you just a straight up histogram of the outcome, right? So there's nothing that can be gleaned from this distribution per se, because this is not the conditional distribution. This is the marginal one. This is just the housing prices, not housing prices left over. But looking at pictures like this can sort of clue you in as to what's going to happen, right? It is really unlikely that after we put in all our predictors, this thing's going to be normal. It's not. So looking at these sorts of pictures can guide us towards which kind of family is going to be most appropriate. I can't do Poisson or negative binomial for this. Why not? Because it kind of looks like a count shape, doesn't it? You know, kind of skewy. Why can't I fit those distributions? SAS won't even let me. It'll yell at me. What kind of outcomes are Poisson negative binomial for? They're for counts. Why is this not a count? It's continuous. What's the difference? Integers. Counts are like 1, 2, 3, 4, and this is dollars. So we have non-integer values. So we have to use a continuous distribution, not a discrete distribution. Counts are discrete. Now that being said, we could go the other way. We could take a count variable and fit a continuous distribution to it. It may not be a great idea, but it would be possible. So here's the model that I'm going to fit in every single version of what we're looking at. My predicted sale price for a house is a function of whether it's new construction. New houses generally cost more. Whether it has 3 bedrooms or 2. Whether it has 3 bedrooms or 4. Whether it has 2 bathrooms or 1, 2 bathrooms or 3. So the manipulation to make all those variables is right here. My choices for this were that my default house is an old house that has 3 bedrooms and 2 bathrooms. That was the most common type of house. So my predictors are coded as deviations from that type of expected house. So what does it do to your sale price if you only have 2 bedrooms instead of 3? What does it do to your sale price if you have 4 bedrooms instead of 3? 1 bathroom instead of 2, 2 bathrooms instead of 3. And then square footage. Square footage is in feet, 1,000 feet. So this is, actually no, take that back. What did I do to it? That wasn't the last thing. Where'd I go? Here it is. Square footage in regular size, so 1,500 square foot is the reference house. I then divided by 100 so that the coefficients wouldn't go all crazy. So my reference house has 1,500 square feet. And then I'm looking at the additional change in price per 100 more square feet. And because more square footage may not matter after a point, I thought there would be some potential nonlinearity there. I am approximating that with a quadratic function of square footage. So you'll get a chance to practice quadratics as well. In the book, he went through this and looked at interaction terms among these variables, didn't find any evidence of that, and I decided this model was complicated enough already, so I didn't do any of that. So, questions on setup? No? All right. So what if we just say it's normal enough, it's fine? So I have 2 different versions of the same model in each program. Let me start with Stata. We're going to get into this next week. Mixed. The analog in SAS, proc mixed. This is software that can be used to fit multivariate outcomes that have a normal conditional distribution. I'm asking it to use maximum likelihood for comparability with the other models. I'm asking it to compute AIC and BIC as a function of 100 houses because by default it does something different. And I'm asking for a multivariate Wald test for whether or not my model is significant. That is the analog to the model R-square test in traditional regression. So let me ask you right here. Is this the same thing as traditional linear regression or not? And if not, why not? So it's made, the assumptions that are underlie the model are made more explicit in GLM. I'm using an identity link and a normal conditional distribution, or Gaussian as they say there. What do you think? Is this linear regression or no? Or general linear models more specifically, or more generally I should say. If I put this in regress, or I put this in proc GLM, proc reg, and SAS, do I get the same answers back or no? Probably. I will get likely the same estimates back. I will not get the same standard errors back, and I won't get the same significance tests back. General linear models are estimated using least squares, ordinary least squares. Ordinary least squares is the same thing as residual maximum likelihood, not regular flavor maximum likelihood. The difference, residual maximum likelihood corrects for the number of slopes that you had to estimate to be able to run the model. Regular flavor maximum likelihood does not. This distinction is only possible in this one instance in which you're dealing with a normal conditional distribution. So because we're using maximum likelihood, the standard errors are going to be smaller than what they would be out of residual maximum likelihood. Another difference is that these tests do not use denominator degrees of freedom. So individual slopes are going to be tested using z instead of t, and groups of slopes like this are going to be tested using chi-square instead of f. So very subtle differences in how this plays out could potentially affect your results. The reason that I'm doing this is because I wanted to keep everything the same across models to the extent possible, which means using maximum likelihood and not using denominator degrees of freedom, because that's what Stata does when you move out of normal models. So here's my output. This is from Stata. And check that thing out. Pearson chi-square over degrees of freedom of 2,907. I've never seen something that bad before. So yeah, normal, not close enough. Decidedly not. What should that number be? 1. I didn't even think it was possible to be that bad. Now, what's interesting about this to me, when you run a regression, did you get this number? No.
Did you ask for it?
No. Only if you run it in this type of software that gives it to you, the GLM software. So yeah, this gives me pause all of the times where I'm like, it's normal, it's fine. This is decidedly not fine. But yes, this is a way that you could get some indication as to whether normal is indeed sufficient, is to look at this. So practically speaking, if I have this kind of way more variance than what the model says I should have, that's going to translate into standard errors, this column right here, that are way too small, because standard errors are based on how much variance your model thinks you have, as well as sample size and the scale of the predictors and their interrelations. So if I just go down the p-value column here, I have a significant effect of new house, I have a significant effect of square footage, the linear effect, and these other ones are not significant. Does that strike you as odd? That it doesn't matter how many bedrooms and bathrooms you have? Yeah, it struck me as odd too, but then I thought, wait a minute, I'm controlling for square footage. The bigger house you have, the more room you have for bedrooms and bathrooms. So this would be a case, not that these things don't matter, but they don't matter anymore, right, after you factor in, like, at the same size house. So, but yeah, this looks like one set of results. I'm not even going to interpret it because this tells me, no, I probably shouldn't be looking at those p-values. SAS agrees. Note the number is different. Stata thinks it's 2907 and SAS thinks it's 2675. So welcome to homework hell, trying to get these things to agree. Here's the same conclusions in SAS, though. The only thing that's significant is new and square footage. So what if I just took the log? Do you remember what a log transformation does? Is a log transformation a linear transformation or a nonlinear transformation? Put the picture back up. If I take the log of this house price variable, what's that do to it? Would you like to see? Why not? I'll do a live demo. That will kill more time. So I'm going to run, I gave you the data to play with here. Make sure that this is going to work. You guys need to move over here so I can see my log. Everything's blue, lovely. Make some predictors, make some stuff. Now let's do proc univariate. Log price. I don't know what the midpoint should be, so we'll shut that off. There we go. Okay, so ready? Original. Error message. This is why Lisa doesn't do live demos. Log price. No, it's there. A variable specified, oh, I know what it is. What did Lisa do wrong? I have size on here for no reason. Actually, that was from the previous one. I need to change this to be log price on the variable list because I only changed it on the histogram statement. Here we go. Ah, look at that. Boom. So what did it do? You were saying, Terry? Yeah, it reels in. It takes the positive skew and just shoves it over there, and it takes the lower side and tries to spread it out. In this case, the lower side can't be spread out much because this outcome is bounded at 0, right? You can't have a house that costs negative money, not even if it's a foreclosure. But yeah, so when you look at that, well, that looks like much more normal-ish. So what the log normal model says is that the log of the outcome is normal. And it kind of looks like it is. Like this is just the marginal distribution, but that looks a lot more plausible. There, live demo.
That's a kind of stupid question.
I love stupid questions.
So, we keep looking at the marginal, like, histogram. Is there a way to spit out conditional, like, inclusion?
Yes.
Okay.
I don't know what it is in Stata, but I know there is a way.
Okay.
It's probably some sort of post-estimation command that you'd have to go look for. It may involve saving residuals to the data set and then plotting them
Okay.
explicitly. There are pictures like that SAS will spit out too. Yep. The only thing is that, I mean, you can look at the pictures and be like, well, that looks good, but you don't have a test or a number that goes with that, which is why trying to rely on this number that's supposed to somehow quantify that picture, I think would be easier in practice. But yeah, you can get that stuff. So yeah, we're going to predict log transforms price. And this is using the same options as before, meaning that we're saying it's an identity link and a normal distribution, but it's on log price instead. And that works out to be the exact same thing as using the built-in log normal in SAS, which Stata does not have. I couldn't find it, at least. It may exist, but I couldn't find it. So this is a workaround. You can log it and call it good. So now we have Pearson chi-square over degrees of freedom about 0.10. So that's much better, potentially a little tiny, but much better than 2900. We have the effect of new is on the fence. The linear effect of square footage is significant, and the quadratic effect is also significant. So let's look at what these things mean. Practice with linear models. This number right here is 4.8. That's my intercept. So what does that tell me? Not a trick. What's an intercept, guys? The expected outcome when the predictors are 0. So this is my reference point for the model, the "you are here" sign of my data, right? So a house that has 1,500 square feet with 3 bedrooms and 2 bathrooms is predicted to cost $40,000. $40,800. This is in $1,000 units. It's in $10,000 units, excuse me. From there, if the house is new, yeah, I'm losing the conversion to $10,000. I think 2,000 more sounds right. It's more expensive. We'll go with that. The number's positive. If it only has 2 bedrooms, somehow it's non-significantly more expensive, which is weird. Maybe it's a condo, like at the top of in downtown or something. Yeah, I don't know about what that is. 4 bedrooms doesn't help. Probably means each bedroom is smaller, which is annoying. If you take away a bathroom, that's cheaper. You take if you add a bathroom, it's also cheaper, which is again weird. But these are after like a half. Yes, yeah. They count halves as wholes in this. There was no half bath, but yes. Now, what do I do with these two things? I don't think we've done this in this class. What do I do with quadratics? There are 4 kinds of quadratic effects, just like there's 4 kinds of interaction terms, because a quadratic term is an interaction term. Remember what those 4 kinds are? Say it with me. More positive, less positive, more negative, less negative. So in general, the main effect of a predictor that's part of an interaction is its effect specifically when the interacting predictor is at 0. The interacting predictor is itself. Whoa. Can you repeat that? That's deep, right? So in general, if you have a predictor that's part of an interaction term, its main effect is specific to when the interacting predictor is at 0. Here, the interacting predictor is itself. Let me get out paint. This is going to take some drawing. Okay. Well, I'm less interested in the p-values than you knowing what to do with the coefficients. Yeah, but I mean, if the quadratic were not significant, you could probably dump it the same as any other higher order term. This term right here you would keep, because if this is significant, it needs this underneath it. This is what's known as the linear effect. So this effect right here, that is the increase in $1,000 per additional 100 square feet at a house that has 1,500 square feet. So in physics terms, it's the line, slope of the line that is tangent to the curve at that point. Now, which pattern is this? What happens to this linear slope, this main effect? This is a less positive. So if I were to draw that, actually that's the wrong way. Less positive. That's a less positive. And what's eventually going to happen to it, according to a quadratic? Yeah. Hang on, that was bad. There you go. I'm very bad at drawing, because you had noticed. So the difference in what the slopes mean, right? If I say 1,500 is right here, like the linear slope is that one. Right there. And it becomes less positive, and here's the rule, by twice the quadratic coefficient. Twice. Because what we're talking about is the second derivative of the function. So the 2 comes down in front. The other way that you can think about it is that there is no other main effect for this interaction term to modify. So it does it twice. So the correct interpretation with this coefficient is that this slope, this 0.08, becomes less positive by twice this number per 100 square feet. So for that reason, the fact that the slope changes as a function of where you are in square footage, even if this were not significant, I keep it, because it's conditional on one particular point. I could ask for what the slope is over here. I could ask for the slope on this side. I could ask for any of the slopes. The linear slope is conditional on the line. There. More fun with linear models. This shows up in models for time a lot more frequently. Growth curve models. You wanted to learn about growth curve models, right? There, that's a whole week on growth curve models. Because time, quadratic time is a very common term to add to make your line a little bendy. So this suggests on the whole that square footage matters less in more expensive houses. The higher up you go in square footage means you're a more expensive house. The differences as a function of square footage and price start to asymptote out. And you could calculate based on these coefficients where that asymptote is, actually. In my book, I have a formula to do that I don't remember off the top of my head. Okay. How are we doing? All right. So here's my SAS output. Same conclusions with respect to new. SAS thinks the p-value is 0.04 instead of 0.05. These two are the same. It thinks the model overall is significant. If I try a different distribution, gamma, instead of log normal, here's another fun fact. GLM in Stata does have gamma, but the log likelihoods don't match the ones in SAS at all. There's a description of why that is in the optional textbook, but basically their routine eliminates the normalizing constant that makes the log likelihood area sum to 1. And so some genius wrote a routine to fix the problem. So I had to go and download something called L gamma that someone wrote to fit this model. And the analog to that in SAS is just to do dist equals gamma. This gives you output that looks a lot like the negative binomial output. You end up with this scaling stretchy factor thing, which we called phi, which is a multiplier of the variance. It changes the length between the variance as a quadratic function of the mean. SAS agrees in terms of the estimates, but look what happened to our p-values across models. So gamma thinks these things are trending into non-significant, whereas log normal thinks that they're fine. I don't know what the right answer is. Do you think it would make sense to do a paper about how gamma and log normal return different answers in this data set? Which one's right? Can I know in any one data set which one's right? What would I have to do to know which one's righter? To try and make like a generalization about this. In this case, we can't look at AIC or BAC because these are different families. The log likelihood is on different scales. The short answer is that I'd have to make up data. I'd have to make up data where I know what the right answers are. And I would probably want to manipulate the data in various ways, like the extent of the stretchy factor, for instance, sample size, that kind of thing, and then see empirically which approach gives me the righter answer. In any one data set, we can't know. It looks either way that gamma fits reasonably well, and so does log normal. So for all intents and purposes, these solutions both seem to be reasonably acceptable, although both of them have a little bit of underdispersion. So that is a dissatisfying answer, but it is the truth. How do you or why do you? How do you? Oh, great question. Would you guys like to learn how to do that? Yeah, that's the basis of quantitative simulation research, where you make up data where you know what the answer is, and you see, oftentimes it's designed to see what is least wrong in terms of bad options to do with it. We all know that small sample sizes make things harder, right? So if you have a small sample size, to what extent do different approaches for dealing with that work differently? The way that you make it up is the way that your homework is generated. For instance, would you like to see this real quick? Why not, right? You're getting to see under the hood. Let's do homework 2 since that one is done. Although that's actually not a great example. Let me do homework 1. How do I do that? Well, you can do this in Stata too, by the way. I just never learned how, because no one's ever asked me before. This is your homework. This is a ginormous SAS file that writes all of the files. This is homework 1. Can I see if I can make it a little bigger? Thanks for helping me kill time, guys. I really appreciate it. There we go. All right. So here's homework 1. Can you guys see this? I can try to make it a little bit bigger. Okay. This is SAS code that grabs your ID numbers. So what I'm doing is giving you each your own data set. Call stream init is how you set a random seed. So whenever you do random number generation, you have to tell it how the randomness started. It's a number known as a seed. Otherwise, it uses the clock, which means you don't get the same answers back if you run it again. To make sure that you guys get the same answers back, I use your ID number as the random seed. That means each of you gets your very own data set, where it's the same information, it's the same parameters, it's just another random version of it. So, do person ID equals 1 to, this is a placeholder for the number of people that are going to be in the story. I'm making up variables. Let's do the first 2 here. Can you guess what this is doing? This is homework 1. This is a variable for the number of publications and the number of posters. I am saying make me this new variable using a random variable that has a Poisson distribution with a mean of 4 or a mean of 5. For quantitative training, I sampled first a variable I called quant from a uniform distribution. Do you know what that one looks like? It's a box. A uniform distribution is a box. It has the same height all the way across all possible values, and they range from 0 to 1. So I created a random variable where every value is equally likely, ranging from 0 to 1. And then I said, if the random variable is less than 0.4, that's going to be my first quant level. Between 0.4 and 0.8 is going to be my second, and then the last is going to be high. So now I have my predictors. I had number of publications, number of posters, and I had an ordinal version of quantitative methods training. Remember this? Low, medium, and high? Or have you blocked it out because it's done? Right? Now here's my logit. I started with a logit of minus 1.5, meaning that getting a job was not very likely. And I decided that for every additional publication, your logit's going to go up by 0.5. For every additional poster, your logit's only going to go up by 0.1. These numbers are within the scale of the variables. That takes usually some guesswork to try and make something that's reasonable. There's no help if you have low to medium quant. There's a lot of help if you go from low to high. And then I have an under additive interaction between quant and npubs, both of them there, meaning that the effective number of publications is less positive if you have high quant training or medium quant training. And that creates my predicted outcome. Now I got to add some kind of error to it. If this were a normal model, I would also add, say, another variable up here for error. For instance, I'd say error equals random normal with a mean of 0 and a standard deviation of, I don't know, 2. I'll make something up, check what happens and change the numbers. But in logits, we don't have an error term, so I don't need that. Instead, what I did is compute my model predicted logit, inverse link it down to the model predicted probability. So that's 1 over 1 plus e to the not logit. That's the shorthand version of the formula. And then I drew another random number between 0 and 1 using a uniform distribution, and I said if my model probability is greater than the random number, then the binary outcome is 1, otherwise it's 0. And that induces error into the prediction. That's how. And then if this were a simulation study, I would have another loop in here that says like do replication equals 1 to say number of reps, where I would do this over and over and over and over and over again. And I would summarize what happened in terms of the model parameters across replications, where these are the right answers. And I would look at things like power or type 1 error rate or accuracy of these coefficients, depending on the situation. So yeah, this is how your homework works. And then I fit your models, save the results, and put them to data sets. There, long answer to a short question. Being able to do this, though, is super helpful in helping you figure out new models, new things. Because if you can make it work and figure out like what SAS or Stata is doing behind the scenes and get the numbers back, that's a really powerful feeling. So making up data is one way to do that. Yeah, anywho.
Hypothetically, do it in Excel too.
Yes, if you're able to control the seed.
Yeah.
Mm-hmm. Yep. You'll see this, actually, yeah, in this lecture, example of a seed. So this is where I was going to talk about quantile regression instead, as an alternative type of approach, where rather than try to predict the mean, I can predict the median or any other quantile. So do you want to talk about that, or you want to talk about if and how much? Zero values. We got 2 topics left. Quantile? Median. Okay. Then I'll skip this stuff for now. Better way of handling outliers. We'll start talking about quantile. Here we go. This is slide 17. So let me back up. What happens in regular regression? So we're out of generalized linear models for right now. But this falls under the category of what else can you do if it's not normal? So in regular flavor regression, what we're trying to do is predict the conditional mean. So if I have, say, an empty model has only an intercept. What's my best guess for anyone's outcome? The mean. That's my guess. From there, I try to refine my guess, make it more custom by taking into account people's values on the predictors. And so the thing that I'm trying to predict, though, is still the mean. It's just a conditional mean. And so that's labeled as y bar. The estimates that you get for the fixed effects, for the slopes, those point estimates, where they come from is by trying to minimize what's known more generally as an objective function, and which in this context specifically of least squares estimation is the sum of squares residuals. So this idea of how far off each observation is from the conditional mean that's predicted, squared, that thing is how you come up with the slope estimates. The standard errors are a function of the residual variance, which back in sums of squares land is this thing right here. And the accuracy of those standard errors rests on the residuals being independent and normal. But back in intro stat, you learned about 3 different kinds of central tendency, right? The mean's one of them. The other 2? Median, mode. Yeah, so what if we wanted to predict the median instead of the mean? The median is more robust to outliers. It's supposed to be a better estimate of central tendency for skewed variables. The difference is what is the function that's being minimized. So rather than coming up with the slopes that minimize the sum of squared residuals, we're trying to come up with the slopes that minimize the absolute value of the residuals. Same idea, very different type of function. So let me go back out of my crappy quadratic. Actually, that's a good picture, though. Sums of squares residuals, that quadratic function would look like this, where you're trying to find the point where that thing is at a minimum, which should be right here. That is equivalent to saying that you want to try to maximize the likelihood. It's the same thing in general linear models. A function that uses absolute value instead looks like this. It's not differentiable. You can't use calculus to figure out if you're heading in the right direction or not. So it has to be solved through algorithms, search algorithms that are not as efficient. They take longer, and having a seed to set them is even more important. So the standard errors, because we're not coming up with some sort of sum-squared error that becomes error variance, we have to do something else to get those. And the something else is usually some form of resampling, one of which is bootstrapping. Have you guys heard of this before? Maybe? Bootstrapping is trying to approximate a sampling distribution empirically. So what it would be in this case is, all right, we run the algorithm, we come up with the slopes, great. Now we sample from our original data set with replacement, do it again. We don't pick everybody, we pick some subset. Do it again, do it again, do it again. And then we have a distribution of what the slopes actually look like across all our samples. That's our empirical sampling distribution. So rather than trying to predict what it looks like using asymptotics, which is where the formulas for standard error come from, we try to do it empirically. And so that does it for you. Because there's all this resampling, in repeated runs of the program, you're supposed to use a random seed to make sure you get the right number back. In all of my programs, I use the same random seed. Does this look familiar to any of you? This is my random seed. Thank you. 8675309. Jenny, Jenny, who can I turn to? This is Jenny, my random seed, always. So yes. Oh, come on. Oh, the young ones here. Okay, your homework is to go to YouTube and educate yourself about Jenny. Yeah. All right, we have 5 minutes left. I'm going to play it out by educating you about Jenny, but I'm going to